unlock the power of Kubernetes and take your GitLab pipelines to the next level. In this video, I show you how I set up GitLab Runners on Kubernetes and how you can do the same to speed up your builds, take control of your workflow, and finally move beyond slow and rigid shared runners. Hi, I am Natalia, a DevOps engineer working with Kubernetes and CI/CD automation. Running GitLab Runners on Kubernetes has completely changed how I manage my pipelines, giving me more control, flexibility, and scalability. In this video, I'll walk you through exactly how I set everything up so you can do the same in your own workflow. Here's what we'll cover in this tutorial. I will start with a quick overview of how GitLab Runners work and which tools we need. Then we'll move to setting up self-hosted GitLab Runner on Kubernetes. After that, we'll optimize performance using overprovisioning. Next, we'll configure storage for our runners, followed by distributed caching to speed up the builds. And finally, we'll configure additional GitLab runners to run a multi-architecture image build with Kaneko. A lot to do, so let's dive in. Before we get hands-on, let me quickly explain how GitLab Runner actually works. Once the GitLab Runner starts, it connects to the GitLab instance and begins its main task, continuously polling for new jobs. Whenever a new pipeline is triggered, GitLab responds by sending a job specification to the runner. The runner then takes the specifications and spins up a new executor to run the job. Now, the executor typically goes through three main stages. First, there is a pre-build stage, where the repository is cloned, caches are restored, and any required artifacts are downloaded. Then comes the build stage, where the actual job script runs. And finally, there is a post-build stage, where caches gets updated and any newly generated artifacts are uploaded. Throughout this process, the executor sends execution logs and job status updates back to the GitLab instance. And once the job is done, the executor is shut down. Meanwhile, the runner doesn't stop. It keeps polling for more jobs. As soon as all dependencies for the next jobs are met, GitLab assigns them to the runner. Each job gets its own independent executor, ensuring they all run in isolation. Logs are sent back to GitLab at regular intervals, and job status updates are updated as soon as each job completes. In this case, yellow job finishes successfully before blue job, and blue job ends up failing soon after. So in simple terms, the runner's job is to poll for new jobs and create executors for each one, while executor is responsible for actually running the job and sending updates back to the GitLab. Now that we have a better understanding of how GitLab runners work, it's time to get our hands dirty and run some ourselves. To follow along, you'll need a few essential tools. First, you'll need a GitLab account. The free tier is more than enough for what we are doing. Then, you'll need a Kubernetes cluster. I'll be using Azure AKS, but you can use any provider you like. If you prefer a local setup, Minikube or K3D will work just fine for most of this tutorial. Next, we need kube control and Helm to interact with Kubernetes cluster. And if you want an easier and more visual way to manage your cluster, you can also install K9s. This is completely optional, but can be quite helpful. For this video, I'll be using DevBox, configured with everything we need. And you can use it too. Just install DevBox, clone the Git repository linked in the description below, and run DevBox shell. The first time you start it may take a little longer as it downloads all necessary tools. So to sum it up, you'll need a running Kubernetes cluster, I'll use AKS, an active GitLab account, and kube control and Helm. I'll be using DevBox configured to have all these tools available. Alright, with that out of the way, let's get started. Let's start by creating a new runner in GitLab. First, we open GitLab and navigate to the group where we want to add the runner. Then, under Build Runners, we can register a new one. Here we need to specify tags that will be used to target this runner in our pipelines. I'll use AMD 64 since this runner will be handling jobs for that platform. You can also add a description for the runner. This is optional, but I highly recommend it to keep things organized, especially when managing multiple runners in the future. Once that's done, we click Create Runner. And on the next screen, GitLab provides us with a registration token. This token acts like an API key. It binds our deployed instance to this specific GitLab runner and authorizes us to execute jobs in this particular group. Make sure to copy this token and keep it safe. GitLab will only show it this one time, and once you close the page, you won't be able to access it again. We start by creating a Kubernetes namespace for our runner and adding the runner token to our cluster as a secret. We will deploy the runner via Helm, so the next step is to add GitLab Helm repository. Now let's take a look at the configuration for our runner deployment. But before that, I need to explain how my Kubernetes cluster is set up. My cluster has 3 node pools. The first one is a system node pool, which has a taint set to critical add-ons only equals true. This ensures that only system-level pods get scheduled on these nodes. Since I want my GitLab runner pods to be treated as system pods, I'll need to add a toleration in the runner configuration to allow them to run here. The other 2 pools are user node pools, one for AMD nodes and another for ARM nodes. The ARM node pool also has a taint to prevent regular workloads from being scheduled on it, ensuring that only the intended workloads run on those nodes. If you want to dive deeper into node taints and tolerations, let me know in the comments. I'd be happy to make a dedicated video explaining them in more detail. But in short, taints prevent pods from being scheduled on specific nodes by default. And tolerations allow certain pods to bypass this restriction if their configuration matches a taint. Now let's take a look at the configuration for our Helm chart deployment. We'll start with the basics. For this setup, we are running just 1 replica, which is enough for our needs. But if you want a more resilient setup, you should run at least 3 replicas spread across multiple nodes for better availability. Next, we have a node selector to make sure the runner is scheduled on a system node. Along with that, we define a toleration, which allows the pod to run as a system pod on one of the system pool nodes. Now, let's talk about security. With RBAC create set to true, the Helm chart will generate a role that allows the runner to create and manage executor pods. By default, if no specific rules are set, this role gets full permission on all resources in the deployment namespace. So in a real-world scenario, you'll want to limit these permissions to only what's necessary. The Helm chart also creates a service account and the required role binding. Moving on to internal runner configuration. This is where we specify the GitLab URL and the secret containing the token we created earlier. Technically, you don't even need a config section at all. But in my case, since I have multiple node pools and I want to ensure that all the executors for this runner are scheduled on the AMD node pool, I've added a node selector inside the configuration. This section is written in TOML format. By the way, if you want to check out all the default values used by this Helm chart, just follow the link shown in the first line of the configuration. It points to the chart source. I've also added that link in the video description for convenience. And while you are there, you'll also find a link to the full documentation of the Kubernetes runner configuration if you want to dig deeper. And that's it for the configuration. Just a quick note before we move on. Throughout the tutorial, I'll be using 2 different shell windows. In one, I'll run the actual commands. In the other, I'll have K9s open, usually focused on the namespace we are working in, so you can see all the running pods. Occasionally, I'll run K9s in both, especially when I need to show different types of resources side by side. Alright, let's deploy our first runner. This will take a little bit of time, but once it's up, we should see it marked as active in GitLab. And there it is. Our first runner is up and running. Now it's time to put it to test by running our first pipeline. I have a very simple pipeline here set up for building a React lead application. It consists of 2 jobs, one for linting the code and another for building the application. The build job only runs if the lint job succeeds, and once it does, it generates an artifact containing the entire build output. To make sure our pipeline runs on the GitLab runner we just deployed, we need to specify a tag. We can either add the tag to each job individually or define a default tag for the entire pipeline. I'll go with the second option. All the files, including the React Vite application and the pipeline configuration, are available in the Git repository link below, so feel free to try it out yourself. Alright, let's trigger the pipeline. Down below you can see the namespace containing all the runner pods, and at the top there is a list of active nodes. The jobs can be triggered manually via GitLab UI and by setting the build variable to UI. As soon as the runner spawns a new executor pod, it starts scaling up the AMD node pool to accommodate the workload. And now the new node is up and running together with the executor pod. The first job has completed successfully, and now it's time for the build job. This time, the new executor pod gets scheduled onto an existing node, so it spins up much faster since the node is already available. And with that, our pipeline has successfully finished running our GitLab runner. Great success! After some time, once the last job has finished, the AMD node is scaled down. This, of course, slows down the next job execution, since a new node will need to spin up again. Now, there are two ways to improve the situation. The first option is simple. You can increase the minimum size of the node pool. This ensures that at least one node is always available. But this approach has some downsides. You can't really predict how many nodes you'll need at any given time, since it depends on how many jobs are running in parallel. In the worst case, you might have too many nodes sitting idle and wasting money, or too few nodes during high load causing delays. The second approach is a bit more advanced, but it helps solve most of these issues. And that solution is an overprovisioning pod. This means we run a dummy pod that stays on a node, keeping it alive even when no jobs are running. You might be thinking, well, isn't this the same as the first solution? Not quite. Here's the difference. In a normal situation, the overprovisioning pod stays on the node indefinitely. So the next job can be scheduled onto the same node instead of waiting for a new one to spin up. But what happens when multiple jobs come in? Eventually, the node fills up and new jobs will have to wait for a new node to be scheduled. But what if we could make the overprovisioning pod step aside when a job needs that space and move it to another node instead? That way, we can always ensure there is one node ready to accept new jobs. And the good news? We can actually do this. The trick is using priority classes in Kubernetes. We'll create a lowest priority class and assign it to our overprovisioning pod. Here's how it works. Whenever a new pod is scheduled, but there is no space left on an existing node, Kubernetes checks if there are any lower priority pods running. If there are, those pods get evicted to make room for the higher priority ones. The evicted pod will then wait until a new node is available or until another higher priority pod finishes. But what about our executor pods? We haven't assigned them any priority class. By default, Kubernetes assumes a priority of 0 for any new pod that doesn't have a priority class set, or if no default priority is configured in the cluster. So, to make this work, we need to create a new priority class with a value lower than 0. In this case, I'm using -1. Then, we need to reference this class in the deployment for our overprovisioning pod. Next, we can control the behavior of Overprovisioner using resource specs. There are two ways to approach this. We can assign small resource requests, allowing the Overprovisioner to stay on the node alongside executor pods, or we can request just enough resources so that the Overprovisioner always gets evicted as soon as a new executor pod is scheduled. For this demo, I'll go with the second option to showcase the eviction process. Now you might be thinking, well, this works great for high load scenarios, but won't it still cost money even when no jobs are running? And yes, that's true. However, you can use tools like kubedownscaler to automatically scale down the overprovisioner during non-working hours, so you are not wasting resources when they are not needed. Alright, enough talk. Let's get this overprovisioner deployed. And there it is. The pod is up and running. To better showcase the eviction process, I will also define resource requests and limits for my executor pods. Without this, Kubernetes might assume there is still enough space on an existing node and schedule additional executor pods there instead of triggering a new node to be created. To do this, we'll need to update our runner configuration. Here you can see the new values, but we'll focus only on the runners config section, since everything else stays the same. Inside runner Kubernetes, we can define resource requirements for the executor pods. The values CPU limit, CPU requests, and memory limit, memory requests set the resource limits and requests for the build container inside our executor. Meanwhile, the values prefixed with helper underscore define resource requirements for the helper container, which handles the pre-build and post-build stages. Alright, let's update the runner. And there it is. The new runner is up and running, ready to take on new jobs. Now let's trigger the pipeline again. And there it is. The overprovisioning pod has been evicted and the executor pod is up and running. Now it will take a little time for a new node to spin up for the evicted pod, but eventually we'll have another node. And there it is. The new node is up. Now let's wait just a bit longer. And as you can see, the old node is gone. So let's quickly recap what we just did. Normally, when a job finishes, the node it ran on gets scaled down, which means the next job has to wait for a new node to spin up. To improve this, we introduce an overprovisioning pod, a dummy pod that keeps at least one node alive. To make sure it doesn't block real workloads, we assign it a low priority class. That way, when a new job comes in, the overprovisioning pod gets evicted to make space, ensuring there is always a node ready to accept jobs. And to avoid unnecessary cost, we can use kubedownscaler to turn off the overprovisioning pod during non-working hours. With this setup, we get faster job scheduling while still keeping our cluster efficient. Alright, that's a good place to pause. I recorded this a bit later, so things look a bit different, that's why. I didn't expect this to grow into such a deep dive, so I've decided to split it into two parts. We'll stop here for now, and in the next video, we'll continue with configuring storage, setting up caching, and pushing things even further. Take a moment to let it all sink in. We'll pick things up in part 2, which is coming soon, so stay tuned.